Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory undergraduate combinatorics based my book, An Invitation to Combinatorics. The subject of this lecture is permutations of multisets and multinomial coefficients. I want to give you a motivating example or two examples, which is actually the bulk of what this talk is about. The rest of the talk will be just putting these in slightly more mathematical jargon. For us, a word is an ordered list of letters. I don't really care about the meaning of a word, mean just a bunch of letters put next to each other, a list. The order does matter though. I might ask the question, how many four-letter words can you make using the letters A, J, and Z? So for example, Zaja or Az would be the two examples of four-letter words that you have used using A, J, and Z. Again, in words, meaning does not matter. This is not that hard. I will count these four-letter words. If you have a four-letter word where you have four spots, spot 1, 2, 3, 4, what can you put in spot 1? Well, you can put an A, you can put a J, you can put a Z. So you have three choices for that first spot. And regardless of which one you use, you again have the same three choices for the next spot. And so together, that's 3 times 3. For every one of those choices that you made for the first spot, you have one of three choices to make for the second spot. So that's 3 times 3, 9 so far. And the same thing true, you have three choices for the third spot and another three for the fourth spot. And so altogether, you will have 3 to the fourth, 81 choices. So 81 four-letter words using the letters A, J, and Z. Another problem, somewhat similar to this, but maybe not, is from among these 81 words, how many of them are just a reordering of the word jazz, meaning that there's a J, an A, and 2 Z's, an anagram. So something like AZJZ would be an example of that. Can we do it the same way as we did before? We do have 4 spots. For that first spot, I do have 3 choices. But then the question is that what's the choice for the next spot? And the choice actually depends on what I did in first. If my first choice is a Z, then I still will have 3 choices for my second spot. But if my first choice is an A, then I don't have an A anymore. And then the number of choices for the second spot will be 2. So I can't use the same normal multiplication principle as I did in the first example and say how many choices for the first one, how many choices for the second one, multiply them, because my choices on the second one depend on my choices on the first one. So what I would have to do if I want to do it that way to make a number of different cases, and in fact, quite a few cases if the problem was larger. So instead, I will do it differently. I will say, first I'm going to place the Z's. Maybe I put them in the first 2 spots, but maybe not. I put them in the first and the third, or maybe the third and the fourth. There's different ways of putting the Z's. And then the question is that, in how many options do I have for placing the Z's? Well, I have 4 spots and I have 2 Z's. So I have to choose 2 out of the 4. And so the number for that is 4 choose 2. 4 choose 2, a binomial coefficient, exactly stands for, and this was a subject of a previous video, how many ways can you make a committee of 2 out of 4 people? Or in this case, out of 4 spots, how many ways can you pick 2 of them? And we had a formula for that. 4 factorial divided by 2 factorial times 2 factorial. 4 choose 2 is actually 6. So you place the Z's, and it doesn't really matter which 2 you pick 2 of them. Now you have 2 places left. And from those 2 places, you have to choose a place for the A. And then from the remaining place, pick a choice for J. And you actually won't have a choice. There will be only just one choice. And so the final answer is going to be 4 choose 2 times 2 choose 1 times 1 choose 1 equals 12. So 4 choose 2, the number of ways I can place the Z's. After I've decided where the Z's go, out of the remaining 2, I pick 1 for A's, and then there's 1 left, and out of that 1, I pick the 1 for J. So that 1 choose 1 is just going to be 1. So again, if you don't know what N choose K is, watch my video on binomial coefficients and combinations of sets. But these 2 problems are the ones that I will now reformulate in several different ways. I really will not add that much content to these 2 arguments. The first one was just a direct multiplication principle, and the second one was this choosing places and then putting other ones. But I will introduce some notation so that we can recognize these problems in different kinds of formats. So let's see. One thing I want to remind you of is what a multiset is. A multiset is like a set, except you allow repetition. So you allow members not to be distinct, and you can have repeated elements. So for example, if a formal definition would be that multiset is a set, but together with a function that assigns to each member of the set a number, a positive integer or an infinity. We allow infinity if we are allowing many copies, as many as you want, of a certain thing. So that's what a multiset is. That integer that you assign to each member of the set is called the multiplicity or the repetition number of that element. So for example, the multiset A, B, C, C, D, D, I really should not use the set notation, but I don't want to clutter it with some other notation, meaning 3 A's, 1 B, 2 C's, and 2 D is an example of a multiset. And it's a multiset whose members are A, B, C, and D, and those have repetition numbers 3, 1, 2, and 2 respectively. So the function that I was talking about is assigning the number 3 to A, the number 1 to B, the number 2 to C, the number 2 to D. So telling me how many copies of each I have. The set is really just A, B, C, D, but I have these repetition numbers. But I actually really like to think of this as a multiset, a set with a bunch of elements. Some of them might be the same as each other. Okay, now let's talk about permutations of multisets. In a previous video, we did talk about permutations of a set when there's no repetitions. Now we are allowing repetitions. So S a non-negative integer, now you have a multiset, a bunch of elements, but some of them repeated. And an S permutation or an S list of T means that you pick S of the elements of that multiset and write them in order. So it's an ordered arrangement of S of the objects of T. Doesn't matter. I mean, and again, there might be repeats depending on what the objects of T are and what their repetition numbers are. So for example, if you had the multiset that had 3 U1s, 5 U2s, and 1 U3 in it, then each one of these U2, U2, U1, U2, or U3, U1, U2, U1 are 4 permutations of T. There are 4 permutations because I put 4 of them in an order, and they're permutations in the sense that the order matters. U2, U2, U1, U2 would be different than U2, 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 U1. Okay, and we want to count these. So our generic set. So let me remind you about if this was a set. Our generic set with T elements is 1 through T, denoted by bracket T. And if I pick an S between 0 and T, then the number of S permutations of this set, this is not a multiset, this is a set, we had a video about this, is going to be just a falling factorial. And the reasoning is just actually like the example at the beginning, but actually a lot easier. How many choices do I have for the first spot in my permutation? Well, T choices, I pick one of those T. And then for the second one, I have T minus 1. For the next one, I have T minus 2. And I have to have S factors like that because I'm making an S permutation. I'm not permuting all elements of T, I'm permuting S of them. And this falling factorial notation, parentheses T with an S, for me means it's a truncated factorial. You start with T and you write S factors of the factorial and then stop. Now, the case we want to look at is not 1 through T, it's not a set, it's a multiset. And the case that I want to look at is when we have infinite repetition numbers, which means that I can use as many U1s, as many U2s, as many UTs that I want. So I have a set that has U1, U2 through UT, but I have as many copies of each of these as I want. So this is a multiset with infinite repetition numbers. And S is again a number between 0 and T, inclusive, and I want to know what the number of S permutations of R is. So how many S permutations does R have? Before I write down the answer, which I should, I want to give you the proof, because regardless of whether or not you remember what the answer is, you should know the argument. And in fact, just stop the video, give the answer yourself. Okay, so I have S spots because I want an S permutation. I have a first spot, a second spot, a third spot, a fourth spot, all the way to the S spot. And I want to put this U1 through U2 there, and I have infinite number of copies. So for the first spot, what can I put? I can put a U1, I can put a U2, I can put any one of them all the way till UT. So I have T choices. Regardless of what I'd use there, there's no restrictions. I can use the same ones or different ones, but any one of the T choices for the second spot. So I have another T choices for the second spot. And again, multiplication principle tells me that I have T times T choices so far. I have another T choices for the third one and another T choices for the fourth one, all the way till the end. And so the answer is going to be T to the S. So the number of S permutations of a multiset with infinite repetition numbers is T to the S. Now, this is just one particular case because we have infinite repetition numbers. And we had done previously the case where the repetition numbers are all ones, because a set is just multiset, just with all repetition numbers one. We had done those two cases. We will do yet another case. We will not be doing the most general case where the repetition numbers are all over the place yet. In a later video using generating functions, and we will tackle this problem again. Okay, so to answer another case, there will be yet another case that I want to answer. I want to introduce a notation, and this is what's called a multinomial coefficient, the generalization of the binomial coefficient. So the number of S permutations of a multiset with repetitions numbers greater or equal to S, I want to, and with T types of elements is T to the S. That's what we said. So what we said was that repetition numbers have to be infinite, but you don't actually need them to be infinite. All you need is that you have to have enough copies more than the permutation you want to make. If you want to make a 47 permutation, then from each element, you have to have 47 or more elements for T to the S formula to work. Because if you have 47 or more, as far as you're concerned, in making your 47 permutation, the number of each element is infinite because you're never going to run out of them. So that's what we just proved. But the question is that, what if the repetition numbers are not infinite, or they're not large enough and you're going to run out of them? And that example that we did at the beginning with jazz was like that. And we could not do the same multiplication principle. So for that, we need this new notation. So you start with a bunch of non-negative integers, n1 through nk, and then you add them up and you get n. Okay, so this is what you're given. You're given a bunch of integers, but then you yourself add them up and you get n. And we define this thing, n choose n1, n2 through nk, to be n factorial divided by n1 factorial, n2 factorial, all the way till nk factorial. And this is what's called a multinomial coefficient. Okay, so always the n on top has to be the sum of the various little n's at the bottom. So note that if k is 2, so if you have only 2 non-negative integers you start with, then you have n choose n1, n2, n factorial over n1 factorial, n2 factorial. But remember, n1 plus n2 is n, so that means n2 is n minus n1. So this is really n factorial over n1 factorial times n minus n1 factorial. And that was exactly our formula for n choose n1. In other words, the multinomial coefficient is a generalization of the binomial coefficient. A binomial coefficient is when you have two things, n1 and n2, and you're finding n choose n1, n2. But you can write down this number. This is a number. I haven't told you what it's good for. I will in a second. But this is called a multinomial coefficient. Okay, so now I'm going to tell you about permutations of a multiset when repetition numbers are not infinite. And again, I'm not going to tell you the most general case. So this is what I'm going to do. So let's say that we have a multiset that has n1 v1s, n2 v2s, and nt vts. So T types of elements, and their repetition numbers are n1, n2, n3, all the way till nt. And n is their sum of those. So that's the total number of elements you have there, clones or not. And you want to find the n permutations of R. So what's special about this case is that you're not looking at a general S permutation. You're not picking another number and saying that I want some of these, but you're going to permute all of them. And that case we will answer now. The more general case will have to wait for stronger techniques, for better techniques. So I want to tell you what that is. But again, I'm not going to tell you what the answer is until I prove you, because I actually want you to stop the video and try to give me the answer, because that if you understood that first example with jazz, you should be able to answer this question yourself. Stop the video, answer it yourself. So again, what I'm going to say is that there's n spots. And again, I'm going to say I can't just go spot by spot. I can't say how many choices you have for the first one. I could say that, but then eventually I might be running out of one of these V1s and so forth. And eventually I will not know how many choices I have, because then it won't be at the beginning, it'll be T choices. And for a while it'll be T choices. But as soon as I go past the minimum of N1 through NT, I will not know how many choices I have, because I may have used up one of the V's when I get there. So instead, what I do is I try to decide where the V1s go. I mean, I put here 2 V1s, but I have N1 V1s. So I place those N1 V1s. Maybe they go here, maybe they go there. I don't know. I'll pick their places. How many ways can I pick out of the N spots? N1 spots for my V1s. And the answer to that is N choose N1. N choose N1 tells you exactly how many ways you can pick N1 spots out of the N available spots. When you're done that, you don't have those spots anymore. It doesn't matter which ones they are. Now you have fewer spots. How many spots do you have? You have N minus N1 spots. And now you want to place V2, and there's N2 V2s. So out of that N minus N1 spots, you have to pick N2 spots for V2. And so how many ways can you do that? N minus N1, choose N2. And these choices are independent of your choices for where to put V1s. So altogether, to place the V1s and V2s, you need N choose N, you have N choose N1 times N minus N1 choose N2 possibilities. You continue, you go on to V3, and you say, well, how many spots are left? Well, before I put V2, there was N minus N1 spots left. Now I put N2 V2s, so now I have N minus N1 minus N2 spots left, and I want to choose N3 of them to place the V3s. So that's the other thing, and I continue like that. And at the last spot, when I'm plugging NT, the VTs, I have the number of spots left is N minus N1 minus N2 minus N3 all the way till minus NT minus 1. And all of those I have to choose NT. Now, if you have been paying attention, you know that N is actually the sum of these things. So if I subtract everything other than NT from N, which is what I've done in this last binomial coefficient, I actually just get NT. And so this is NT choose NT is actually 1. That last one, there's only NT spots left, and I have NT VTs. I've got to just put them on those spots. So there's just only one way of doing it. But okay, but this is sort of a little bit ugly. Let's expand it a little bit, and might be like, why would you want to expand those binomial coefficients? But if you do, something nice will happen. So let's see. What is that N choose N1? Well, N choose N1 by a formula we have for binomial coefficients. Watch the video on combinations of sets, counting subsets, and binomial coefficients. It's N factorial divided by N1 factorial times N minus N1 factorial. Okay. What about the second factor, N minus N1 choose N2? Well, that's N minus N1 factorial divided by N2 factorial times N minus N1 minus N2 factorial. And then one after that is starts with N minus N1 minus N2 factorial, then N3 factorial at the bottom, and then N minus N1 minus N2 minus N3 factorial. I just didn't have room to put that. And you just continue. And the last one is going to be N minus N1 minus all the way till NT minus 1 factorial, NT factorial. And then when you subtract that last NT from that, you actually will get 0, because N is N1 plus N2 all the way till NT. So N minus that will be 0, and 0 factorial is 1. Now, why did I write that in this fashion? Why would you do that? Well, because I noticed that N minus N1 factorials cancel. So do the N minus N1 minus N2 factorials. And in fact, the cancellation goes all the way through. And the only thing left is N factorial, or N1 factorial, N2 factorial, N3 factorial, NT factorial, and 0 factorial. But 0 factorial is just 1. So the answer is going to be the multinomial coefficient. So the number of, if you have a multiset, a whole bunch of things, and you want to write down all their permutations, if you want to permute all of them, you can't just pick and choose. I haven't told you how to do that. But if you want to permute all of them, then the answer is a multinomial coefficient. And that's sort of an easier way to remember it than doing this argument again. But you should always know the arguments and not just the final answer. That's going to be a lot more useful, a much more transferable skill than just knowing about your formulas. Okay, so here's an example. Say you start with the word Shahriari, and you try to permute the letters and in that, and you want to know how many words you're getting. And meaning doesn't matter. How many ways can you, when you permute that? Of course, if you switch the place of the two H's, nothing will happen. It's the same word, so you didn't get a new word, or the two I's or the two R's. But if you switch the place of A and R, for example, or scramble it all together, presumably you'll get a different word. How many words can you get? And again, words that don't mean it, that have nothing to do with meaning, just a list of letters. And so what we want is that these are 9 letters there. And so we want the 9 permutations of one S, 2 H's, 2 A's, 2 R's, and 2 I's. And again, this is a multiset, and I want the 9 permutations, and that's the total number there. And so I know what the answer is. The answer is going to be a multinomial coefficient. 9 choose 1, 2, 2, 2, 2, and that's 9 factorial over 2 factorial to the 4th, 2 factorial to the 4th. It's just 2 to the 4th, and the answer is 22,680, assuming that I've done the calculation correctly. Okay, now let's translate this problem to balls and boxes so that we can recognize slightly different problems in the format of the 2 problems about permutations of multisets that we have seen. If you have S distinct balls and T distinct boxes and no capacity restrictions, and always with balls and boxes, you want to put all the balls in the boxes, and you want to know how many ways you can do that. So you have S different balls and T different boxes, and how many ways can you put the balls in the boxes? And there's no, you can leave a box empty if you like, or you can put all the boxes in one box, ball in one box if you want, or you can distribute it more evenly, whatever. How many ways can you do that? Now, if you think about it, so think of the balls as 1 through S. They have a number on them, ball number 1, ball number 2, ball number S. And when you put a ball in a box, you're choosing that box, you're picking that box, but you're also assigning a number to it. What number? The number that was on the ball, because the ball was different than the other ball. And so you put it in there. And that number is going to tell you where in a permutation that box is going to go. So putting a ball in a box chooses that box and assigns a position to it. Like it says, this is the 3rd one, because you put the ball number 3 in there. If you put ball number 3 and 5 in the same box, then that box is going to appear in position 3 and position 5. And so each placing of balls in the boxes, when you're done and put all the S balls in the boxes, you are going to get an S permutation of the boxes. Maybe not all the boxes. S could be less than or equal to T, but you get an S permutation of the boxes, and that's the same as the number of so that's the number of ways of playing balls in the boxes, and the answer is T to the S, as we saw previously. The argument for T to the S isn't that hard either. You have S distinct balls. How many choices do you have for the first ball? T choices. How many choices do you have for the second ball? T choices. T choices. T to the S. Again, the argument is often easier than other things. The point here that I'm trying to make for you is that you can always translate one of these balls and boxes to this without any problem. Now here's another balls and boxes problem. I have N distinct balls and T distinct boxes, and you want to put N1 balls in the first box, N2 balls in the second box, and so forth, NT box in box number T. So again, this is different than the previous one. In the previous one, you were putting there was no capacity restrictions. You could put as many balls in any of the boxes as you wanted to. Here, that's not the case. You want a specific number of balls in each boxes, and N is the sum of these. So you're putting all your boxes in all your balls in the boxes, and you know exactly how many in which box you can put. So the balls are going to be 1 through N. Putting a ball in a box, again, chooses that box and assigns a position to it. So again, each placing of balls in boxes is the same as a permutation of a permutation. When I say a permutation or an N permutation, that means I'm permuting everything. I'm not just picking and choosing. This multiset that has N1B1s, N2B2s, and NTBTs. And as we saw, the number, so therefore the number of the ways of placing balls in the boxes is the same as the permutations of that, and that's N choose N1, N2 through NT, N factorial over n1 factorial, n2 factorial to nt factorial. And again, you could do the same argument. You could say, let's decide where the B1s are going to go. And out of those, like which balls are going to go indoor, and count each one of those separately and multiply those binomial coefficients, just like we did for counting the permutations, and you would get the same answer. But the point is that you can translate the balls and boxes problem, this balls and boxes problem, this specific balls and boxes problem, to the question of permutations of a multiset with repetitions numbers n1 to nt. But when you want a permutation of that size. That's the end of this lecture. Not quite. I'm going to go back now and say that first example that I had at the beginning, and I'm going to remind you how that translates to what we did. So we said how many four-letter words using letters A, J, and Z, and that's the same as number of form permutations of a multiset with infinite repetition numbers, because I can use A, J, and Z as much as I want, or the number of ways of placing 4 distinct balls in 3 distinct boxes. The 4 distinct balls are the 4 spaces in your permutation. The 3 distinct boxes are a box for A, a box for J, and box for Z's. And you can put as many as you want in any box, and there's no capacity restriction. And the answer was 3 to the 4th equals 81. The other question was that how many words are a reordering of jazz? And that's the same as the number of 4 permutations of this multiset 1A, 1J, 2Z. And as we saw that this is a multinomial coefficient for choose 1, 1, 2, and the answer is 12. So the point here is that you've done 2 types of permutations of multisets. One case when all the repetition numbers were infinite. In that case, we just got a power, t to the s. The other case where we are permuting everything and not picking and choosing, and in that case, we get a multinomial coefficient. This is the end of this lecture. These are some other lectures along the same lines that might be of interest to you. This was the permutations of multisets and multinomial coefficients lecture. Before this came one on counting permutations of a set, one on circular permutations, one on combinations and binomial coefficients. And after this, there will be one on combinations of multisets and counting integer solutions. Till next time.